Hello everyone. Welcome to week 3 code walkthrough for DLCV course, Deep Learning for Computer Vision. We'll be starting in 2 minutes. I'm waiting for students to join. Once I'll wait for 2 minutes if anyone is planning to join, and then I'll start. So this week we'll cover the week 3 for deep learning for CV course, which covered neural networks, feed forward neural networks and back propagation, gradient descent its variant, regularization in neural network, and improving training of neural networks. So we'll discuss some of the topics in this code walkthrough. We'll wait maybe one more minute so if anyone is planning to join, and then I will start the session. Okay, I think only one person has joined, so I can start. So, in this code walkthrough, we'll be discussing about neural networks. These are first set of import statements are standard import statements, time, random to set the random seed, numpy, pandas library, and matplotlib to plot the uh, training curves and all. And then we have some python specific import statements. So basics of python, it's a python based scientific computing package. It's a replacement of numpy optimized for the to be used for the gpus, and it provides a deep learning platform that has significant flexibility and speed. At its core, it has a similar multidimensional array object, which is called tensor, but with GPU acceleration. It also provides a optimized autograd engine for computing derivatives, and it provides a clean and modular API for building and deploying deep learning models. So let's start with how you can create or construct a tensor directly from some other common Python iterables like list or tuple. First example here, we have a list of three elements 0, 1, 2, and we want to convert it into a tensor. We can simply use this torch.tensor function and turn this one dimensional list to a tensor. Then similarly, what we can do is, we let's say we have a tuple of tuples. Same thing we can do with this also, torch.tensor of b to convert it into a tensor. And suppose we want to create a standard array of, let's say, two-dimensional standard array of size 2 times 3 with all values 1. So easy way one way to do is first create the array in multi-dimensional array or n-dimensional array using numpy and np dot ones, and then convert it into a tensor. PyTorch also provides this uh, capability inherently also. So instead of using np dot ones and then doing torch dot tensor, you can directly create a tensor of ones using torch library, which is the next thing. The numerical argument we pass to these constructors determine the shape of the output. So we have ones constructor, zeros constructor, or empty constructor, which will basically create, like, whatever size will pass to this, or whatever shape will pass to this constructor, that will create a tensor of the same size. Uh, we PyTorch also provides the constructors for random numbers. For example, to generate a uniform distribution or sample from uniform distribution, you can use torch.rand rand and just pass the shape of the tensor you want to generate. Similarly, you can use torch.randn to generate a tensor of, like, if it's a two-dimensional tensor or a three-dimensional tensor. So what this will do is, let me run the first part. Okay. Okay. So the currently import statements are running. Okay, done. So what this torch.random does is it samples from a uniform, like standard normal distribution, and then if you want particular mean and variance, then you can do the reparameterization trick to update, like add whatever mean you want and divide it by or multiply it by some number to change its variance. Then PyTorch also provides constructors to construct a tensor using, but with basically dimension equal to another tensor. So instead of passing the shape as 1 3 or 3 4, you can directly pass a tensor variable, and it will consider whatever is the shape of that particular tensor. It will just create a zeros tensor or random tensor of the same size. So the format of it is like, instead of using torch dot zeros, we are the function or the constructor we are calling is torch dot zeros like. Okay. Then to reproduce the outputs in PyTorch, we what we can do is we can use this torch.manual seed to seed the random number generator for all devices, whether it is a CPU or GPU. So once you set the manual seed, whenever you do the random number generation, it will generate the same random number every time. For the custom operator, for the Python custom operator, you can do the random number random dot seed zero for for the Python operators. And for NumPy library, you can do NumPy dot random dot seed. So for any code you are running, for reproducibility, you need to set you need to set these three seeds: the torch manual seed, the random seed for Python custom operators, and the numpy random dot seed for the numbers generated using numpy library. So here we are doing nothing but just a function that controls the randomness. It will just do the all the manual seed for like torch and so first we are randomly choosing a seed, then setting the random seed for Python, then NumPy random seed, and then these are all the reproducibility statements. So torch.manual seed, torch.coda.manual seed all, and torch.coda.manual seed. These will set the seed for the torch random number generator. And in torch there are some functions which are like inherently non-deterministic. So for to make sure that you if you will be able to reproduce your outputs, you need to set this. If you are using GPU device, then you need to set this torch.backends.cudnn.benchmark as false and deterministic as true. Once you set this deterministic as true, you will not be able to use any algorithm or any function which does not have a deterministic version to run. So there are some functions or some classes for which there is no deterministic formulation. those you will not be able to run. So now let's see this, set the seed function in previous example and execute the multiple times to verify if numbers are printed are always same or not. So let's see, let me run it from here, here. Okay, I've run the function. Now we have a function which we are first we are setting the seed here and then generating the random numbers from the uniform distribution and normal distribution. And let's see, when we call this function we get some output, right? 0.464963, and from some Gaussian distribution, right? And if we run this or call this function again, we'll get the same output. So our output will not change because we are setting the seed. Suppose we don't set the seed and we change this to false, our output will change every time we run this. So now you see, now it is generated for tensor A. The first element is 0.0362. Now if I run this again, my output will change. You can see output has changed. So I have lost the reproducibility because I have not set the seed. Okay. Then Python also PyTorch also provides this number ranges, just like in NumPy, the arrange and linspace functions. So you can do torch.arrange and you can pass basically this 0 to 10. So 0 is your start point, then 10 is your endpoint, and step is taking by default 1. You can always update this step to something like 2 or 3, and same way for B also. B is numpy a range variable. Same way you can do with linspace, start and end and steps. So you can see that the difference, only difference between the two is that numpy array is 0 to 9, it's a array, but the first one, the torch.arrange, is returning a tensor. Okay. Then you can perform some operations on tensors using methods under torch. So you have, so basically you can use torch.add, and this only works if C and D already exists. So if you do out equals to C, then this will work only if C already exists. Like C. So you see here, if I comment C, I'll get some error here. No. Oh, okay. I think so. I, because I had run it like previously, I think it was, one second, right? So is there a C somewhere? If I do del C and if I do C here, now C doesn't exist anymore. And let's see. Yeah, you can see that once I deleted C, it is asking me that the name C is not defined, but I can always remove this argument out equals to C and just do this. Let me comment this. Let me comment this also. Comment this also. Now, so now what I have to do is I have to store it in some variable C equals to. I just cannot do directly like using out equals to C. So I have to assign the values to some other variable or other tensor. Okay, then PyTorch also follow the all the Python operators are overridden in PyTorch also. So it will follow the common standard arithmetics like plus, minus, multiplication, division, and exponentiation. So other things is your tensors have some methods called sum, which basically if you don't pass the axis or the dimension, then it will just sum over all the elements. But if you pass the axis and dimension, it will sum over the particular row, like all the rows or columns. Okay. So this is, I think, very standard. Then we have a at the rate symbol to represent matrix multiplication. You can also use torch.matmul. Uh, Also, you can do the transpose of a matrix or a 2D tensor using dot t parenthesis or dot capital T. Uh, so yeah, tensor dot t capital T is an attribute, not a method. That is why the parenthesis is not there. This one is a method. Then these are all same things. Dot product also you can do. Huh. So PyTorch also follows the same standard slicing methods which we had done for the standard Python operations, Python list and the arrays and tensors. So if let's say suppose you have a 1D 10 element array, you want to only access the last element, so you can do x of -1. Suppose you want the second element to second and third element, then you can do 1 to 3. And suppose you want only the element up to the penultimate, like just before the penultimate or the second last element, so you can do all -2, like before -2 whatever elements we have. You can also create multidimensional tensor same way as you did in the NumPy. uh, Say it also follows the flatten and the reshape operations. uh, so I'm not going to go into details. Also, there is a method called dot view that is used to reshape the tensors. There is a subtle difference. There's a very subtle difference between view and reshape, but in this particular code walkthrough we are only going to use the reshape method. You can also squeeze the tensors. For example, this is a 1D tensor, but we have added one dimension which is not adding, like just a single, like we have made it a vector or a matrix of 2D size or 2D shape. What we can do is we can squeeze it using this parenthesis, like the square bracket. Like we can choose the first element of this first row of this matrix, or you can use the squeeze function to basically squeeze particular dimension. So we can get rid of the singleton dimension this way. We can also add a singleton dimension using unsqueeze, or what you can do is, suppose you have done the squeeze operation. Let me do this. Okay, so now you see here that x has a shape 10. Suppose I want to add singleton dimension at let's say second dimension. So what I can do is I can do all comma none. This is your Python standard Python operation, and if you look at the shape of this, it will be 10 comma 1. Yeah, you can see 10 comma 1 here. uh, Unsqueeze simply adds the dimension, but you can do the unsqueeze using this method also. Sometimes our dimensions will be in wrong order. For example, when we are dealing with RGB images, we have sometimes we have channel first, but we want the channel to be last. So for that, you can use a permute method for a tensor. So suppose we have a 48 cross 64 matrix with 3 channels, and we want the channel to be a last dimension, not the first dimension. So you can simply do x dot permute 1 to 0. So what this will do is it will permute the basically it will make the zero dimension to be a third dimension, and the first dimension to be a for like the second dimension to be first and third to be second. So zero, yeah, same thing. Zero dimension of my new tensor is the first dimension of old tensor. First dimension of my new tensor is second, and second dimension of new tensor is zero. You may also use transpose for this, but then transpose you have to pass the dimensions, which dimension you want to like do the exchange. This works similarly as perpute, but you can only swap 2 dimension at once. So you have to basically do multiple transpose to do that. Sometimes if it's a high dimensional tensor, you can concatenate two tensors using torch.cat method. Uh, you can also convert it into like you can go from a float tensor to a numpy using numpy function, or you can go from numpy function to the tensor using torch.tensor. Also, you can convert a size1 tensor to a scalar, and using the dot item only works for us one size 1 tensor. If you try to do it for, let's say, uh, 2.5, I'll get a dot item will give me error that a tensor with two elements cannot be converted to a scalar. So this will not work, but float of a and float or int of a will work, so that is fine. Then suppose you have created a tensor in PyTorch or in Torch, and you want to work in the GPU, not in the CPU. So let's say we create a tensor. So by default, it is creating a tensor in CPU. If you want to, okay. So first of all, if you're working in Collab, you have to go to runtime here. You have to do go to change run type here, and you have to basically choose which you tensor or CPU or tensor you want to work with. Here by default I have chosen T4 GPU, but you can choose TPU or CPU, or if you have a pro version then A100 GPU or other things. Okay. So when then after choosing the runtime in CUDA, if you do torch.cuda.is underscore available, it will return true. This is true for your system also. That in your system, if there's a CUDA available, you need to do this torch.cuda.is available to know whether your CUDA device or GPU device is recognizable or not by whatever library CUDA library you have installed. Then you can basically use this set device function, or it is nothing but it is just a if condition that if torch.cuda is available is true, then it will take device will take the value or string CUDA, else it will take the string CPU. And then you just need to do this. So when you are so there are two ways to send your tensor to a GPU device. Either while creating a tensor you can choose the device, or you can do this dot to device, whatever device you have, like a string CUDA or string CPU, to change your or send your tensor to particular device. So both works in the set device. Okay, I have not removed the function. Yeah, so both functions works in the same way. Either you can do it while creating the tensor, or once you have created the tensor and you want to send it to GPU, you can do that also. Note that the type of tensor changed after calling dot to. What happens if we try to perform operations or tensors on devices? We cannot combine CUDA. So now once we have sent our device to CUDA, or if our device or particular tensor is in CPU, it's not possible to work with one particular tensor being in CPU and one tensor being in GPU. So you both the tensors should be on same device, otherwise it won't work. So here we are giving the example for that only. So here what we are doing is, let's suppose X is in GPU, Y is in CPU, and Z is again in GPU. So one way to do it is, let's say suppose you want to do your transformation or whatever operation you want to do, you are want to do in CPU, so you can transform or transfer your X to CPU. You can do the operation. And other ways, you can transfer your Y which is in CPU to device which is GPU and do the operation. Okay. So this is the reference for this particular section. Now let's move on to neural networks. So again, neural networks, suppose we create a toy data set. We create a toy data set. 100 items are there, two-dimensional items are there. It's a binary classification data set which has two classes. Each class has 50 points. Okay, and we have make sure that we have normalized the data so that it has zero mean and unit variance. So we do this. This is how our data looks like. And if we look at the test set, the test set looks like this is the training set. Okay. Now, suppose we want to implement a perceptron model using NumPy. So what we have to do is we have to define a number of features we want. We have to define the weights and the bias. Then we have to do the transformation W transpose X plus B, and then prediction is wherever my linear value is returning positive value, that will be 1, and else it will be 0. The backward propagation also you have to implement the backward function, and the train function is simply you basically calculate the error and update the weights based on the errors, weights and bias based on the errors. Okay, so when we do this, you can see that model parameters initially are like not initially. Okay, so APN underscore numpy dot. Okay. Okay. So let's say uh, we have some initial weights which are starting from 0, which we have initialized here. Bias is also 0 after running for 5 epochs on this particular data set, which this data training set. When we run this for 5 epochs, we get some weights and some bias. Now, if we look at the accuracy of training accuracy, it's 100%. But if we look at the test accuracy, it's 93.3%. And if we plot the decision boundary along with the train and test data, we can see that uh, like here you can see, right, orange classes are little, like two of the points in orange class are misclassified, right, in the test data. Now, same thing, let's implement using PyTorch. So, suppose we set the device to be CPU. We have a perceptron torch class. We define number of features. We initialize the weights through 0 and bias through 0, and then we have a function, a placeholder vector. So self dot ones and zeros. Then we do the matrix multiplication using torch.mm, and basically the step is W transpose X. And again, prediction is wherever our output is greater than 0, that will return 1, else 0. Backward is also same way we implement the backward function, and then training is simply updating the weights based on the errors. Okay, again we do this thing, and we see if we want to compare. So we can see that because we started from same initialization, both NumPy version and the PyTorch version gives us the same set of weights: 1.27, 1.34 minus 1, 1.27, 1.34 minus 1. So here also we know that the test accuracy is also 93.3%, and the decision boundary also will look same. Okay. Now, this was the perceptron example. Now we move on to feed-forward neural network and backpropagation. Again, some import statements we have, and to plot, basically plot the decision boundary, we have a helper function here, and we have also have a contour plot in this one, which will plot and shows the direction of the steepest ascent. So gradient descent algorithm, as we know that given a function, we will calculate the gradient with respect to particular parameter and then update based on like the gradient descent rule, because we know that the in the negative direction the function decreases. So this is, I think, standard. So this plot simply shows for the function, this function, sine of x square plus y square, sine of x square plus y square, the direction at different points in our space, the input space, what is the direction of the steepest ascent. The gradient vectors are showing the direction of steepest ascent. Ascent means increasing direction. If we do the negative or the different, like the negative of this particular direction, or we go in opposite direction of our gradient, that is the direction of steepest descent. Okay, so we can see from the plot that for any given x naught and y naught, the gradient vector points in the direction of x and y for which z increases the most. So if we go in the opposite direction of gradient vector, then we'll know that the function or z value decreases in that particular direction the most. So it is important to note that gradient vectors only see their local values, not the whole landscape. Also, the length of each vector, which indicates the steepness, can be very small near the local plateaus. Okay, so gradient descent algorithm is very simple. Suppose we have a function mapping from RD to R, d-dimensional real numbers to a real number, and it is a differentiable function. The gradient descent is an iterative algorithm that starts with some initial value of w, takes steps of size eta, which is also called learning rate or step size, in the direction of negative gradient from the current point to update the variables. So that is our gradient descent algorithm. So in PyTorch, so deep learning frameworks such as PyTorch, TensorFlow come with a very efficient and sophisticated set of algorithms known as automatic differentiation. So like till now, whatever whenever we needed this gradient value, we were implementing the back, like the backward function, right, for perceptron. But PyTorch provides this auto gradient or automatic gradient, which which you can use to calculate the gradients instead of writing your gradients, like gradients on your own. So everything starts with forward propagation. You do the forward propagation, you create a computational graph that I will show next, and the PyTorch tracks all the instructions as we declare the variables and operations, and it builds the graph. Then we call backward function. Then PyTorch rebuilds the graph every time we reiterate it or change it. So PyTorch basically uses a dynamic graph. So every time we build a graph, PyTorch will change the graph during the iteration. That doesn't happen in TensorFlow. I think the TensorFlow 2.0 they have added this functionality of dynamic graph, but before, like if you are using the older version of TensorFlow, this will not happen. So that is why TensorFlow always you have to first create a graph and then you have to realize the graph. Without that, it doesn't work. For gradient descent, it is only required to have the gradients of cost function with respect to variables. So these variables are also called trainable parameters. In neural nets, weights and biases are all often called learnable parameters. So building a computational graph is very easy. So to indicate a certain tensor contains learnable parameter, we can set the optional. So to inform the PyTorch AutoGrad engine to say that we want the gradient for certain variable, all we need to do is set this argument requires underscore grad to be true for that particular tensor, and PyTorch will then track every operation using this tensor while configuring the computational graph. So suppose for w and b we want to calculate the gradient, so we'll set the required grad true for them, and then what will happen is PyTorch will just track. So what we are doing here is we are taking input x, multiplying it with w, adding b, applying tan h over it, subtracting y from it, and then squaring it. That is our loss, right? So simple regression loss or mean square error loss we have here. Wx plus b provides a prediction. Tan h is the activation function, and then we do the subtraction, right? So we do the square loss, and initial weight is minus zero point 0.5, initial bias is zero point 0.5. So for x equals to 1 and y equals to 7, L2 loss is 49. Okay, so till now we have not done the backward propagation. Till now we have just created a computational graph. It is so important to appreciate the fact that PyTorch can follow our operations as we arbitrarily go through classes and functions. This just means that you can add any set of functions or call any object or operations, the user defined operations here, and PyTorch will keep track of all those operations. So now we'll see how the autograd works. So in PyTorch, tensor functions are interconnected and build up a acyclic graph that encodes the computational history. Each variable has a grad function attribute that references a function that has created the tensor, except for tensors created by users. Those have none as grad function. Example below shows c equals to a plus b created by add operation, and the gradient function is, so you can see right here that when we created the graph, and if we look at the gradient grad underscore function of c here, it just shows that which function was which operation was implemented last. So for more complex function, printing the grad function would only show the last operation. Suppose you are doing multiple operations, applying multiple activation functions, and then finally doing something, or for that matter, for this one, right, only thing it will return is this. So the backward function will have is the last operation we applied, which was square, like power, right? Other thing is, right, yeah, you can see power backward here. So now, just to test whether, because it's a very simple W transpose X plus B, and then we are doing the mean square error, um, uh, we can simply calculate the analytical gradient of loss with respect to W and B, and same way we can get the gradient using the PyTorch engine by calling the backward function and then calling W, like that particular variable dot grad. And if we try to match those, if they match, then it will this operation, right, equality, like matching it, will return true, else it will return false. So if we run this, it will return true. That means the mathematical known gradient is same as what PyTorch is calculating for both W and B. Okay, so now we know how the autograd works in the PyTorch. So now let's move on to how we can implement it. So uh, some import statements. Then we have a function for plotting. Then this is the same function which we had defined before for setting the seed for reproducibility. Then set device function which we had used before. Now PyTorch provide a neural net module, NN.module, which is a ready-to-use neural network building block, such as linear layer, recurrent layer, different activation functions, loss functions. And if we build a neural network using torch.nn layer, the weights and biases are already in required grade, so you don't have to implicitly initialize the parameters. Once you create the layer, the PyTorch backend PyTorch, the variables will be initialized, the parameters will get initialized. So for training, we need three things: model.parameters, which refer to all the learnable parameters of the model, which are accessible by calling dot parameter. So you create a object of the class inheriting ending dot module, and then you call this dot parameters function on that object. You will basically get all the parameters. Please note that not all the required grade tensors are seen as model parameters. To create a custom model parameter, you can use this ending dot parameter function, which will just convert your standard tensor into a module parameter. Then you need a loss function, which you will be going to optimizing, like a mean square error or zero one loss. And then you will also need the optimizer, which PyTorch also provides different optimization methods. Optimizer holds the current state of the model and calls the step method to update the parameters. Okay, so suppose we have this data set and we want to apply regression here. We define a wide net. Wide net just means that we have a single layer with 512 neurons. We have a tan h activation function, and then we have the output, which is the scalar because regression. Okay, so now Y seed. Okay. Okay. So now here we are doing the set seed to ensure the reproducibility. Then we define the or create a object of wide net class which we had defined before. We can see that it has first layer, it takes input 1 like scalar value, hidden dimension is 512, bias is true, then we apply tan h activation, then it outputs a scalar. We can use the neural network module in PyTorch to get the MSC loss function. You can say like define it on your own also, just to make sure that you don't have to define the PyTorch like the backward function, or you don't have to manually create the gradient. You always use the PyTorch define operations. Okay, so you can't do numpy dot sum and then expect the PyTorch to calculate or create the gradient. You have a learning rate 0.003, and PyTorch like torch.optim provides different optimizers. Here we are using SDD. You just need to pass your parameters which you want to update or do the gradient descent on. You pass your learning rate and the momentum. Uh, you do this. Huh. So first step we have to do is we have to reset the gradients of all the gradients to zero for the optimizer. Then we do the forward pass, then we calculate the loss. So forward pass will give us the prediction on the random, like first step it will be random weights, then we do the loss, calculate the loss, then we loss dot when then we do the loss dot backward, and then we do the sgd optimizer dot step. So you can see that the loss we have printed is 0.675. Why reset all the gradients is zero? If you don't do this, and when you do the second step of gradient descent, without this, what it will do is it will store the gradients, and it will it will keep on accumulating your gradients for each step. So what this will do is it will make all the gradients zero from the previous step. So in the training loop, that is what we are doing. Every epoch, you make the gradient zero, you do the forward propagation, calculate loss dot backward, optimizer dot step. That is your training loop. Okay. Okay, x3 plot. I define this. So if I run this, so you can see here the second plot shows how the training error is going down. Here we had run it for 1847 epochs, but our learning rate was very small. That is why it is going so small. But you can see that how the prediction, the red curve in this particular first plot is working. It's very close. Then suppose if you want to understand different variant of gradient descents in PyTorch, suppose we do the MNIST classification. So PyTorch, Torch Vision, you can get standard data sets such as MNIST or CIFAR 10 or CIFAR 100, or it provides different standard data sets. So here I am just loading the MNIST data set. You can simply do it using Torch Vision data sets and whichever data you want. It will download that particular data set. You can set the training argument true or false to depending on whether you want a training set or test set. And we simply create a data set. And if we look at some of the images here, you can see that this is how the data looks like. 6 is there, 3 is there, 7 is there. So it's a 10 class classification. Again, we create a my MLP class with nn dot module as its parent class. uh, then we define some layers. define some layers. Okay, so here suppose we just simply we don't want any hidden layer, then we'll simply go from 784 dimensional, because our input is 28 cross 28 dimensional image. So that is why we are going we and this is not CNN, this is multi-layer perceptron. So we are simply flattening out our images and we are going from input to output directly. There's no activation, nothing. Single layer input, single layer model. This we do, you can see input is 784, output is 10. Then suppose we define the loss to be negative log likelihood. We implement the gradient descent, zero grad, we make the gradient zero grad. These are the standard functions which we had. uh, Okay, so now in the previous step, we were using optimizer to update the parameters. You can manually update the parameters, but make sure that when you do this, you put this whole thing under this with torch.nograd, because otherwise, your PyTorch engine will keep on adding this also as your part of your computational graphs, just to make sure that we don't want gradient for these operations. We add it in under this with torch.nograd, and if we do this, we can see that the parameters are updating. It starts from something and update happens. This was the standard gradient descent. We have huh. So, but torch.optim provides your you with like standard SGD with momentum, SGD with momentum, and Nestru momentum, AdaGrad, Adam, RMS prop, and Adam. So we can simply try to see how they works, and right. So this just shows how different optimizers work. This is not required here. It's not required. Yeah. So I think this was the code walkthrough for your week 3. If you have any questions, you can ask me now. And if you have any doubt in any of the concept which we have discussed today, you can ask me now also. Or any logistical issue or anything. Okay, then if there are no doubts, then I think we can end the session. I will end the recording now and we can end the session. I will end the live stream also. Thanks for joining.